Jacob Lano, and this is Lab 2 Projectile Motion. Purpose of this lab is to demonstrate how objects interact with gravity and how they change due to velocity with time. This is because of Newton's second law and the velocity update equation with gravity. Here we have the uh, experiment itself. I am throwing the system, which is a paper ball, and the surrounding is gravity, which is so it's the Earth, and drag, which is also the Earth. And here we have the graphs of the physical and actual uh, experiment, along with the XY positions in time. Um, the model versus real life. The first model, which is made out of code, is talking about just the velocity change due to gravity. The second one is going to be more accurate because it talks about drag as well. This is the actual physical um, data of the experiment itself. So the second model will look more like this. Here are some helpful equations: the velocity update, gravity, drag, again, the system and the surroundings. Code. Here we have the first model, which is, as you can see, there is no drag, so this position versus time is not changing. Um, we found that due to the initial velocity, delta time interval, um, gravity itself, and then the F net, which is just the change in velocity due to gravity, and then again the velocity update with position update right here, and then a time interval, and all of the other things are just able to visualize. And then here we have the second one, which is including drag. As you can see, is not a perfectly consistent change in x, which means that it is going to be more accurate to the real life data. And this is changed due to the implementation of the drag coefficient, which is uh, on the right here, negative b times v squared times direction of v. So it's changing due to the direction, which means that it both affects the y and x, which is, as you saw, the not consistent x. Um, Sources of error could have been if the y, x, and if the axis of the physical got data was not on the ground, so the y didn't end up at zero, and if it wasn't directly below um, the start, which means that the x was not initially zero, or if the person threw the ball in the z direction out or in, could have affected it as well. And also, for code wise, a source of error could have been if it was not set up correctly, as in the F net, or if the any of the equations were not set up. What if questions, the terminal velocity, in this case, terminal velocity happens whenever the gravity is balanced out by the drag, usually in a straight down falling motion. After a certain amount of time, the drag will catch up with the velocity of gravity, which means that the system itself will not be speeding up anymore. This does not happen in this case because there is not enough time of the fall for the drag to be as efficient. And then what if the ball was thrown up straight up into the air? Will it take longer? Yes, it will take longer because there is a higher peak, which means it takes more time to go down, besides it being more flat and across, which is a lower peak, which means even though it's going farther in the x direction, the y is still so much lower. Thank you so much, and that was my presentation.